Today, we confront a question that seems simple but shatters everything we think we know about reality. Why can't we zoom in forever? I want to start with something simple. Something so ordinary, you probably have not looked at it closely in years. I want you to look at this piece of chalk in my hand, and I want you to look at the desk in front of you, and the air you are breathing right now. To our eyes, the world looks smooth, does it not? The chalk feels continuous. If I run my finger along the desk, there are no gaps, no holes. It feels like a solid, singular thing. If I pour a glass of water, it looks like a continuous sheet of blue fluid, bending and flowing without a break. We have this intuition, born from 2,000 years of living on a human scale, that matter is stuff. Just continuous stuff, like cheese. Like if I cut the cheese, I have smaller cheese. If I cut it again, smaller still. And we assume that this smoothness goes all the way down. But I am here to tell you that this intuition is a lie. It is a trick of scale. If we could improve our vision, if we could zoom in, not just 10 times or 100 times, but 1 billion times, that smoothness would vanish, it would shatter. The world you think you know would dissolve into a catastrophe, a chaotic, beautiful catastrophe. Let us take that drop of water in your mind, magnify it, zoom in. At first you see the surface getting rough, and then you see it is not a sheet at all. It is a crowd, it is a mob. It is billions upon billions of distinct little particles, molecules piled on top of one another, and they are not sitting still. This is the most important thing I can tell you today. Nothing is still. Down there at the bottom of the teacup, it is a jiggling, vibrating mess. These water molecules are banging against each other, bouncing off one another, twisting, turning, vibrating, billions of times a second. We call this heat. That is all heat is. It is not a fluid, it is not a ghost, it is the jiggling. When you heat up your coffee, you're just kicking the molecules and making them jiggle faster, making them bang into their neighbors harder. And this has consequences. Why does the water evaporate? Why does the sidewalk dry up after the rain? We do not see the water flying away. But if you were down there, you would see it. You would see that every once in a while, one of these molecules gets hit by its neighbors, bam, 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 and it picks up just enough accidental speed to fly apart from the crowd, to break the attraction of its friends, and zip. It flies up into the air. That is evaporation. It is a mechanical accident in a chaotic game of billiards. So the first thing we must accept is that matter is granular. It is made of atoms. Now, I use the word atom, and you have a picture in your head. We all do. You see the picture in school books, a little solar system, a nucleus in the middle, and little electrons orbiting around like planets. It is a useful picture, but it is also terribly misleading about one specific thing: scale, the size of the thing. You cannot comprehend how empty an atom is. Let us try to build a model. Let us say we want to build an atom that is big enough for us to see. So we take the nucleus, the heavy part in the middle, the protons and the neutrons, and we make it the size of a marble, a simple glass marble. Now, to build the rest of the atom to scale, how big does the atom have to be? If the nucleus is a marble, the atom is the size of a professional football stadium. The nucleus is the marble sitting on the 50-yard line. And where are the electrons? They are gnats, tiny, invisible gnats, whizzing around in the highest row of the bleachers. And what is in between the marble on the grass and the gnats in the stands? Nothing. Empty space. This is the shock of the atomic theory. The floor you are standing on is mostly emptiness. The chair you are sitting in is empty space. You are made of empty space. If we took all the actual matter, the nuclei and the electrons out of every human being on Earth and squashed it together so there was no space left, the entire human race would fit inside the volume of a sugar cube. So this begs a question, does it not? A very serious question. If the atom is a stadium of empty space, why cannot I walk through the wall? If I lean on this desk, why does not my hand, which is mostly empty space, pass right through the desk, which is mostly empty space? It should be like two clouds passing through each other, smoke through a screen door. But it feels solid. Knock, knock, it hurts my knuckles. Why? It turns out the emptiness is not exactly empty. It is filled with fields, and specifically electric field. The electron may be a gnat in the beaches, but it has an electric charge, and because it moves so fast and because of the rules of quantum mechanics, which we will get to, it creates a cloud of influence. It is like a propeller blade. When a propeller spins fast, it looks like a solid disk. You cannot put your hand through it, not because the blade is everywhere at once, but because it spins so fast it defends the whole space. The electrons in my hand are negatively charged. The electrons in the desk are negatively charged, and nature has a rule. Like charges repel, they hate each other. So when I bring my hand close to the desk, the electrons in the desk start pushing back against the electrons in my hand hard. The closer I get, the harder they push. That solid feeling, that sensation of touching something, you're not touching the nucleus. You're not touching the matter. You're feeling the magnetic and electric repulsion of the fields. You're feeling the force field. You're hovering, actually. You're hovering 100 millionth of a centimeter above the chair you're sitting on, suspended by the electrical repulsion of the atom. Now, I have to correct myself. I have to be honest with you. I told you the electrons are like gnats. I told you they are like planets. That is the classical idea. That is the picture we had in 1910. But as we looked closer, as we tried to pin these things down, we found out that nature is far more mysterious than a little solar system. We've found that if you try to find exactly where the electron is, you cannot. It is not a hard little ball. It is not a gnat. It spreads out. It behaves like a wave. It is a smudge of probability. It is a cloud. In the football stadium analogy, the electron is not a bug flying in seat 402. The electron is a sort of ghost that occupies the whole stadium at once. It is here, it is there, it is everywhere in the stands simultaneously until you try to catch it. So we have this picture now. We have the jiggling world of heat. We have the empty cathedral of the atom held together by stiff electric fields, but we still have a problem of fundamental curiosity. I can break the chalk into dust. I can break the dust into molecules. I can break the molecules into atoms. I can break the atom into protons, neutrons, and electrons. But can I keep going? Look at the electron, this thing that carries the charge, this thing that creates the structure of chemistry. What does it look like if we zoom in on it? Does an electron have a front and a back? Does it have a skin? Is it made of gears and wheels inside? Or is it just a point, a zero-dimensional dot of pure geometry? If I take a knife, a metaphorical knife of high energy, and I try to slice the electron, what falls out? And this is where we run into the Great Wall. This is where physics stops being about things and starts being about information. Because to look at something that small, you need light. You need to shine a light on it. But light itself has a punch, and when you are looking at something as tiny and fragile as the fundamental particles of the universe, the act of looking changes the thing you are looking at. Now we have to pause. We have to stop and think about what we are actually doing. I told you that we are going to look at the electron. I told you we are going to zoom in on the atom, and you nodded. You accepted that. Because in our everyday world, looking is free. Looking is gentle. Looking does not cost anything. If I look at you sitting there, I do not hurt you. I do not push you. The light comes down from the ceiling. It bounces off your nose. It goes into my eye, and my brain says, aha, there is a student. You do not feel the light hitting you. It is a very delicate touch. It is the gentlest thing in the world. But this intuition, this idea that we can watch the world without disturbing it, is completely wrong when we go down to the basement, when we go down to the scale of the atom. We have to ask, what is seeing? What is the mechanism of vision? To see something, you must hit it with something. You have to throw something at it and wait for it to bounce back to you. Usually we throw photons, we throw light. Now light behaves like a wave, like the ocean. It has crests and troughs. And the distance between two crests is what we call wavelength. This is important. Keep this in your pocket. The wavelength determines the size of the thing you can see. Imagine you're standing at the edge of a harbor. The ocean waves are coming in, big rolling waves, maybe 10 meters between the crests. and there is a giant ocean liner anchored in the harbor. When the waves hit the ship, what happens? They bounce, they reflect, and they create a shadow behind the ship. If you were standing on the shore looking at the pattern of the waves, you would say, hey, there is something big out there disturbing the water. You can see the ship using the waves. But now imagine there is a tiny cork floating in the water, a little piece of wood, maybe an inch wide. The big ocean waves come in. Do they bounce off the cork? No, they do not even notice it. The cork just bobs up and down. The wave goes right over it and continues on its way unchanged. You cannot see the cork with the ocean waves. The tool is too clumsy. The wavelength is too big. If you want to see the cork, you need smaller waves. You need ripples. You need to make waves that are smaller than the cork itself. This is the rule of the microscope. If you want to see a beetle, you can use visible light because the waves of visible light are tiny compared to the beetle. But if you want to see an electron, now we have a problem. The electron is tiny. It is absurdly tiny. So to see it, to resolve its position, we need a light wave with a wavelength that is incredibly small. We need to tighten the wave. We have to compress it. We have to move from red light to blue light to ultraviolet to X-rays and finally to gamma rays. We need a wave so short, so sharp that it can bounce off an electron. But nature creates a trap here, a trade-off, and it is a brutal trade-off. There is a formula. It was discovered by Max Planck and Albert Einstein. It is very simple. Energy equals a constant times the frequency. What this means in plain English is this: as you make the wavelength shorter, the frequency goes up, the wave shakes faster, and because it shakes faster, it carries more energy. Red light is lazy, it has low energy. Blue light is energetic. X-rays are very energetic. Gamma rays are ferocious. So here is the dilemma. This is the tragedy of the physicist. To see the electron, to find out exactly where it is, I have to use a very short wavelength. I have to use a gamma ray. But a gamma ray is not a gentle ping-pong ball. It is not a feather. A gamma ray is a sledgehammer. It is a bullet. So let me give you an analogy. I want you to imagine a room. It is completely dark. And on the floor of this room, there is a tiny, delicate beetle crawling around. You want to know where the beetle is, but you cannot turn on the lights. You have a bucket of balls. First, you try throwing ping-pong balls. These represent long wavelength light. They are soft. They are gentle. You throw them into the dark. Poof, poof. Most of them miss. Finally, one hits the beetle. Boing. It bounces back to your hand. You say, aha, I felt the bounce. But because the ping pong ball is big and fuzzy, you do not know exactly where the beetle is. You just know it is somewhere over there in a general area. The ball is too big to give you a sharp picture. You have a blurry image. So you say, this is not good enough. I want precision. I want to know exactly where the beetle is, down to the millimeter. So you put away the ping pong balls, you reach into your bucket, and you pull out a heavy steel marble, a ball bearing. This marble represents a high energy light. It is small, it is hard, it is precise. You throw the marble into the dark, you throw it fast. Crack. You hear it hit, you calculate the angle. You know exactly where the marble struck. You shout, I found it. I know exactly where the beetle is. But then you turn on the lights. And what do you see? You see a smear. You see a tragedy. You hit the beetle with a steel marble traveling at 1,000 miles an hour. You found where the beetle was, yes, but in the act of finding it, you walloped it. You knocked it clear across the room. You imparted so much energy to the beetle that you have completely changed its speed and its direction. Before you looked, the beetle was crawling south at a slow pace. After you looked, the beetle is flying north at the speed of sound. By asking, where are you? You destroyed the answer to where are you going. This is the Heisenberg uncertainty principle. And I want to be very clear about this. This is not just a problem with our tools. It is not that our microscopes are bad. It is not that our fingers are clumsy. Even if we had the eyes of God, this rule would still hold. It is written into the fabric of the universe. Werner Heisenberg wrote it down like this. Delta X times delta P is greater than or equal to H bar over 2. Delta X is the uncertainty in position. Where is it? Delta P is the uncertainty in momentum. How fast is it moving? The equation is a seesaw. If you push down on delta x, if you try to make the position very precise by using a high-energy photon, the other side, delta p, shoots up into the sky, the momentum becomes wild and unknown. If you try to measure the momentum gently using soft, long waves, delta p goes down, but delta x shoots up. The picture gets blurry. You cannot have both. You can never, ever know both. Nature protects her secrets. She says you can look at the face of the electron or you can look at the movement of the electron, but you cannot look at both at the same time. So what does this tell us about reality? What is the philosophical punchline here? It tells us that the concept of a precise path is a lie. In the classical world, the world of baseballs and planets, we think of things moving in a line. A planet orbits the sun. We know where it is now, and we know where it will be in 10 minutes. It has a smooth trajectory. But down there, in the basement, there are no smooth lines. Because if you cannot know the position and the speed at the same time, you cannot draw a line. You cannot say it went from A to B. The electron does not move in a straight line. It wiggles, it jitters, it explores all possible paths. It is a cloud of probability. When we are not looking at it, the electron is not a thing at a specific point. It is a wave that is spread out. It is a smear of potential existence. Think about foam. Sea foam. From a distance, the ocean looks flat. But if you get close into the foam, where is the surface? Is the bubble part of the water or part of the air? It is fuzzy. The boundary is not sharp. Matter is like that foam. If you try to zoom in on the edge of the table, you think you will find a sharp line. Hard wood, then empty air. But because of Heisenberg, if you zoom in far enough, the edge gets fuzzy, and the electrons in the wood are not staying on their side of the line. They are leaking out a little bit. The air is leaking in. The boundary dissolves into a haze of uncertainty. There is no sharpness at the bottom of the universe. There is only the jiggle. There is only the blur. So we have hit at a wall made of logic. We wanted to slice the chalk forever, but now we see that we cannot even hold the chalk steady enough to slice it. The more we try to hold it, the more it shakes. The electron fights back. It refuses to sit still for its portrait. But human beings are stubborn creatures. Physicists are the most stubborn of all. We do not like being told no. We say, okay, Heisenberg, I get it. I cannot look gently, so I'm going to stop being gentle. I'm going to stop using marbles. I'm going to use trains. We build machines, colossal machines, the cyclotrons, the synchrotrons, the Large Hadron Collider in Geneva. They ring 17 miles around, buried under the earth. We take protons, the hearts of atoms, and we speed them up faster, faster, round and round, kicking them with magnets until they are traveling at 99.99999% the speed of light. They have the energy of a mosquito flying, but packed into a subatomic speck. And then we smash them together, head on. We do not try to see the beetle anymore. We try to explode the beetle. We want to see what flies out of the wreckage. We want to force the universe to give up its inventory list. And when we do this, when we smash the proton open, what do we find? We were taught in school that the proton is simple. It has 3 quarks, they said. 2 up quarks and 1 down quark. A nice, neat little package. Rubbish. That is a lie for children. When we crack the proton open with the energy of the Large Hadron Collider, we do not just see 3 quarks. We see a soup. A boiling, bubbling, chaotic soup. It turns out the inside of a proton is not a quiet room with 3 people sitting in it. It is a crowded dance floor. Yes, the 3 quarks are there, but holding them together are these sticky, stretchy things called gluons, the glue of the universe. And the gluons are flying back and forth between the quarks at the speed of light, carrying the strong nuclear force. But it gets worse or better, depending on how you like your physics. The energy inside that tiny space is so high and the quantum uncertainty is so wild that new particles are popping into existence out of thin air. Quarks and anti-quarks, they appear out of nothing, pop, they live for a billionth of a second, and then they annihilate each other, zap, and turn back into energy. They are called sea quarks, the sea of virtual particles. The proton is full of ghosts. If you took a snapshot of a proton, you would not see three simple spheres. You would see a storm. You would see a fluctuating blob of energy where matter is being created and destroyed constantly. The mass of the proton, the mass of you, does not come from the weight of the quarks. The quarks are tiny. They weigh almost nothing. 99% of your mass comes from the energy of that storm inside the proton. You are not made of stuff. You are made of the energy of motion, trapped in a box. You are made of fields tying themselves in knots. Now, we have to change our thinking completely. We have been talking about particles. I have been saying quarks and gluons and electrons as if they are little marbles, as if they are little dots that move around in empty space. But this picture, the particle picture, is actually a little bit old-fashioned. It is a placeholder. The real truth, the truth of the mid-20th century, the truth of quantum field theory, is much stranger. I want you to imagine a mattress, a vast, infinite mattress that covers the entire universe. It has springs, rows and rows of springs, all connected to each other. Now, if I hit the mattress in one spot, what happens? A wave ripples out, the springs jiggle, the energy moves through the mattress. In modern physics, but there are no particles, there are only fields. The mattress is the field. There is an electron field that fills the entire universe. It is everywhere. It is in this room. It is inside your nose. It is in the space between the stars. What we call an electron, the thing we think of as a particle, is just a twang on that field. It is a localized vibration. It is a knot of energy moving through the mattress. When an electron moves from point A to point B, it is not a little ball rolling. It is the excitation of the field transferring from one spring to the next. And there is not just one mattress, there are many. There is an electron field, there is a quark field, there is a gluon field, there is a photon field. That is the electromagnetic field. They are all stacked on top of each other, all occupying the same space. And here's the magic. The mattresses are coupled, they are tied together. If I jiggle the electron field, say I wiggle an electron, it pulls on the photon field. It creates a wave in the electromagnetic field. That is how light is made. An electron wiggles, and it shakes the photon field, and a light wave comes out. So the universe is not a box of marbles. It is a layered ocean of fields. And what we call matter is just the music of these fields. We are the foam on the waves. This leads us to a very disturbing conclusion about empty space. Go out into the deepest part of the cosmos, between the galaxies, remove every atom, remove every photon, make it absolute zero, make it perfectly dark. Is it empty? No. Because the fields are still there, the mattress is still there. You cannot get rid of the mattress. And because of Heisenberg, the mattress cannot be perfectly still. If the field was perfectly still, its value would be zero, and its rate of change would be zero. Heisenberg says, forbidden. You cannot know both zeros at once. So the field must jitter. It must hum. Even in the dead of space, the quantum fields are vibrating with a zero-point energy. This means that empty space is actually a hive of activity. It is boiling. If we could zoom into the vacuum, to the space between the atoms, we would see virtual particles appearing and disappearing. Think of it like a bank. The universe is a very strict bank. The law of conservation of energy says you cannot create energy out of nothing. You cannot have an overdraft. But quantum mechanics says, well, maybe the bank manager is asleep for a millisecond. If you borrow energy very, very quickly and pay it back before anyone notices, you can get away with it. So a particle and an antiparticle pop out of the vacuum. They borrow the energy to exist. They live for 10 to the negative 21 seconds, and then they collide and pay the energy back. They vanish. This is happening everywhere, right in front of your nose, inside your brain, in the vacuum of space. The vacuum is frothing with these temporary particles. We call this quantum foam. And we know this is real. This is not just philosophy. We can measure it. There is something called the Casimir effect. If you take two metal plates and put them very, very close together in a vacuum, so close that the bigger waves of the vacuum cannot fit between them, there are more virtual particles pushing on the outside than on the inside. And the plates get pushed together by nothing, by the empty space. The vacuum has pressure. The vacuum has power. The nothing is actually a very heavy something. So let us take stock of our journey. We started with the chalk. We found it was made of atoms. We found the atoms were mostly empty space. We zoomed into the empty space and found fields. We looked at the fields and found that they are boiling with virtual particles. The closer we look, the more violent it gets. When we look at the world with our eyes, it is calm. When we look with a microscope, it is jiggling. When we look with a particle accelerator, it is a storm. Now let us try to push it to the limit. We are currently down to about 10 to the negative 18 meters. That is the scale of the quarks. That is the limit of our best machines today. But we are theoretical physicists. We have pen and paper. We can imagine going smaller. We want to find the bottom. We want to know, is the mattress continuous, or is the mattress itself made of little distinct springs? Is space-time smooth, or is it pixelated? We want to zoom in to 10 to the negative 35 meters, the Planck length. We feel pretty good. We think we solved the atom, we solved the nucleus, we solved the fields. We just need to build a bigger machine. If we build a collider the size of the galaxy, we can pump enough energy into a photon to see that small. We are ready to see the ultimate pixel of reality. But nature has one last card to play, and it is the joker. It is the force we ignored, the force we thought was too weak to matter. Gravity. You see, in all of our quantum field theories, in all this talk of quarks and gluons, we left gravity out. Because gravity is feeble. It is weak. The electric force between two electrons is 10 to the 42 times stronger than the gravity between them, and gravity is a whisper in a hurricane. But gravity has a rule. Gravity feeds on mass. And remember Einstein? Mass is energy. If I want to look at something very, very small, 10 to the negative 35 meters, I need a photon with a wavelength that's small. But a wavelength that's small means a frequency that is insanely high. And a frequency that high means the energy is astronomical. To see the Planck length, I need to pack the energy of a freight train into a space smaller than a proton. And when you pack that much energy, that much mass into that tiny space, gravity suddenly wakes up. Gravity stops being a whisper, becomes a monster. The curvature of space-time becomes so strong that it curls up around the photon. You are trying to illuminate the particle, but you've put so much energy into the light that the light collapses under its own weight. You create a black hole. And this is the paradox. This is the wall. If I try to look closer, I need more energy. If I use more energy, I make the black hole bigger. A bigger black hole swallows more of the view. By trying to zoom in, I have created a horizon that prevents me from seeing. I am no longer looking at the fine details. I am looking at the event horizon of a microscopic monster I just created. The harder you squint, the darker it gets. This is the Planck wall. It seems to be the place where the universe says, stop. So let us push it to the absolute limit. Let us do a thought experiment. Forget about money. Forget about engineering. Suppose we are advanced beings, gods of physics, and we build a particle accelerator the size of the entire observable universe. And we want to look at the Planck length. There's 1.6 times 10 to the negative 35 meters. A decimal point, 34 zeros, and a 160. To give you a sense of scale, if you took an atom and magnified it to be the size of the entire universe, the Planck length would be about the size of a single tree on Earth. That is how small we are talking. Now, according to our rule, to see that distance, to get a wavelength that short, we need a photon with an energy that is absolutely colossal. And this is where the trap snaps shut. This is where the two great theories of physics, quantum mechanics and general relativity, crash into each other and have a car wreck. You fire your super high energy photon to illuminate this tiny, tiny point. You concentrate all that energy into that tiny volume to see it. But because the energy density is so high, the gravity becomes immense. Space-time curls up around that point. It wraps around itself. You know what you just made? You did not make a microscope. You made a black hole. It is a tiny black hole. Sure, it evaporates almost instantly. But for that split second, it is a true black hole. An event horizon forms around the very thing you're trying to look at. And what does a black hole do? It swallows information. It prevents light from escaping. So the photon you sent in to bring you the picture, it gets eaten. It never comes back. You do not get a sharper image. You get darkness. And if you say, I will try harder, I will put even more energy in, then you just make a bigger black hole. You make the event horizon larger, and you see even less detail. This is the ultimate wall. This is the bottom of the barrel. Nature is telling us that there is a fundamental limit to measurement. If you try to probe distances smaller than the Planck length, you destroy the geometry of space you are trying to measure. It suggests that distance simply does not exist below that scale. It suggests that space-time is not a smooth sheet, it is pixelated. And once you hit the pixel size, you cannot zoom in anymore. The screen just goes black. So what does this tell us about the stage we are walking on? We used to think of space as a container, a box. You put stars and atoms inside the box. The box is just there. It is geometry, Euclid's geometry, XYZ, smooth, continuous. But this experiment with the black hole tells us that the box itself is made of something. And if you push it too hard, it breaks. At the Planck scale, the concept of position melts away. You cannot say the particle is here and the particle is there, because the distance between here and there is dissolving into a quantum fog. We call this space-time foam. This was John Wheeler's idea. Imagine you are flying in an airplane over the ocean. You look down. The ocean looks like a flat blue sheet. Smooth. Curves slightly with the Earth. This is general relativity. Smooth geometry. Now jump out of the plane with a parachute. Get closer. When you see the waves, the surface is rough. This is the atomic level. Now splash into the water. Put your face right into the surf. What do you see? You see foam, bubbles, turbulence, water crashing into air, air crashing into water. The definition of surface disappears. You cannot tell where the ocean ends and the sky begins. It is a frothy mix of both. That is what space-time is like at the bottom. It is not a smooth sheet. It is a turbulent, boiling froth of geometry. Space is tearing apart and stitching itself back together. Little wormholes. Bridges from one point in space to another might be opening and closing constantly. Topology is changing. Left and right, up and down, before and after. These words belong to the world of the smooth ocean. They do not belong to the foam. In the foam, cause and effect might be tangled. In the foam, the very notion of distance is fluctuating. This is where physics, as we know it, ends. We have hit the bedrock, or maybe we've hit the hole in the floor. Now, some people find this depressing. They say, Professor, you are telling us there is a wall. You are telling us we can never know what is at the bottom. But I do not see it that way. I think it is marvelous. Think about what this implies. It implies that the universe is not continuous. It implies that the universe is pixelated, or to be more accurate, it is informational. There is a maximum amount of information you can pack into a region of space. That is what the black hole limit tells us. You cannot pack infinite detail into a finite box. This connects physics to computer science. It connects gravity to thermodynamics. It tells us that space and time are not fundamental. They are emergent. Just like heat is not a thing, heat is just the motion of atoms. Maybe space is not a thing. Maybe space is just the result of something else, with something deeper tangling together. Maybe space is like the temperature of the universe. It is a statistical average of the quantum foam. We are standing at the edge of a great cliff. Behind us lies the world of atoms, the world of quarks, the world of smooth geometry that Einstein gave us. Ahead of us, over the cliff, is the Planck Scale, the land of quantum gravity. We do not have the theory yet. The string theory tries to build a bridge. Loop quantum gravity tries to build a raft. but we do not really know. And that is the most exciting place to be. We have taken the chalk and we have crushed it until the universe refused to let us crush it any further. We found that the smoothness of the world is a lie, and that the bedrock of reality is a jittering, boiling, foaming storm of uncertainty. Nature has protected her deepest secrets with a wall of black holes. And she is standing there smiling, saying, if you want to see what is behind this wall, you're going to have to get a lot smarter. I think we will. But for now, that is the end of the line. So I'm going to put the chalk down. We have reached the end of the line. We have reached the bottom of the page. And I want you to sit with this feeling for a moment, this feeling of hitting a wall. You see, we started this lecture with a very simple question: what is the world made of? And we had a very simple human intuition. It is made of stuff, hard stuff, like this desk, like that rock outside. We thought that if we just kept cutting, we would find a smaller piece of hard stuff, a smaller rock. But the universe has played a magnificent trick on us. We zoomed in. We found molecules, then atoms, then nuclei, then quarks. And finally, we hit the Planck scale. And what did we find? Did we find a tiny, hard, indestructible grain of sand at the bottom? No. We found a storm. We found a jitter. We found a set of laws that prevent us from seeing any further. This tells us something profound about reality. It tells us that the universe is not made of things. It is not made of nouns. It is made of verbs. It is made of events. It is made of interaction. An electron is not a thing. It is a behavior of a field. Space is not a thing. It is a network of relationships. At the very bottom, matter melts away, and what is left is information, limits, rules. Now think about the way we have done physics for 300 years. Since Newton, we always imagined a stage, a theater stage. The stage is space and time. It is rigid. It is wooden. It is there before the play starts, and it is there after the play ends. And on this stage, we have the actors, the particles, the forces. They run around. They say their lines, they bump into each other. But the stage never changes. The stage just sits there and holds them up. But this journey to the Planck length, this collision between gravity and quantum mechanics, it ruins the theater. Because when you zoom in that far, the energy becomes so high that the stage itself begins to warp. The floorboards start to buckle, the wood begins to splinter and dance. The actors are shaking the stage so violently that you cannot tell which is the actor and which is the stage anymore. This is the great crisis of modern physics. We do not know how to do physics when the ruler we use to measure the distance is also jiggling and changing length. How do you measure a wiggle with a wiggling ruler? So this leads to a very strange idea, an idea that is very popular with the young theoretical physicists today. Maybe space and time are not fundamental. Think about heat. What is heat? Is heat a fluid? No. Heat is just the average motion of a billion atoms. If you have one atom, it is not hot, it is not cold, it just is. Temperature only exists when you have a crowd. Maybe space is like that. Maybe down at the Planck scale, there is no such thing as distance. There is no left or right. There is just a network of connections, a web of information. And when you zoom out, when you step back and look at the whole web from a distance, it looks smooth. It looks like space. It looks like the empty air between you and me. Space might just be the heat of the quantum connections. Geometry might be an accident of large numbers. That means the stage is an illusion. We are walking on a collective hallucination of quantum gravity. So what is underneath the illusion? If the floorboards are fake, what is holding them up? We have guesses, beautiful guesses. Some people, the string theorists, say that if you could look past the Planck wall, you would not see particles at all. You would see tiny, vibrating loops of energy, strings. And just like a violin string, if you pluck it one way, it vibrates as an electron. If you pluck it another way, it vibrates as a quark. If you pluck it differently, it vibrates as gravity. The universe in this view is a symphony, a cosmic orchestra playing a tune on 10-dimensional instruments. There is no matter, there is only music. Other people, the loop quantum gravity folks, say no, no, no. They say space is like chainmail. It is made of interlocking loops. It is a fabric. You cannot divide it forever because eventually you get to a single link in the chain. You cannot have half a link. Space is quantized. Who is right? I do not know. They do not know. And this is where I want to leave you. Some people get scared when they hear that we do not know. They want answers. They want the textbook to be finished. But I think that is a terrible attitude. Look at where we are. We are standing at the edge of the cliff, looking out into the fog. We can hear the ocean crashing down there, the quantum ocean. But we cannot see it yet. It's not that wonderful. It means the game is not over. It means there is still work to do. Nature has put up this wall, this Planck wall, not to keep us out, but to tell us you need new ideas. Our old ideas about geometry, about points, about lines, they do not work down there. We need a new imagination. We need a new generation of crazy thinkers to figure out what the universe is doing in the basement. So do not be disappointed that we cannot zoom in forever. Be delighted that the universe is deep enough to hide its secrets from us for a little while longer. The chalk stops here, the measurement stops here, but the thinking, the imagination, that goes on forever. Nature says that is enough looking for now. Go home and think about it. Thank you.